Hey physics students, welcome back to another edition of Rapid Review for Honors Physics. Today our topic is about sound. We're going to talk about the concepts of interference, beats, and Doppler shift. But before I start, I need to just put out a disclaimer, maybe it's an apology. The way to get most of your learning about sound is to experience it, to hear it in the classroom, to listen to demonstrations. If you don't have access in school, you could do that. You could find things on YouTube. I'll link to a few of them. And with apologies, I will not do many actual demonstrations in this presentation, mostly for technical reasons. Oh, and while we're on the topic of sound, we have invited here at the studio, above me, we've invited some air conditioning technicians to stomp around on the roof and make sounds for atmosphere. If you hear that, you'll know what it is in the background. In the meantime, we will forge on with our content. I want you to consider interference in one dimension. Let's say along a line. Okay, so maybe I have a speaker set up and it's sending a wave out to the right along the x-axis. I mean, sure, it spreads out vertically too, but I'm just going to look at the x-axis and think about that longitudinal wave traveling to the right. I'm going to indicate the squeezy parts with a red line. Okay, that's, we would say more correctly, vocabulary, compression of air and stretching out, rarefaction. I like squeezy and stretchy, so I'm going to use that. I think it's just easier to say. So here's my squeezy parts moving to the right, and as you might expect, lambda is the distance between the two squeezy parts. Now, to make it interesting, at one moment in time, I'm going to show you what's happening with a different wave happening at the same time, same frequency, as you can see, because the wavelength is the same in green. So there's a red wave and a green wave traveling towards each other. They meet in the middle, and then, of course, they continue on. There's a person in the middle, exactly in the middle, at a point where the waves are meeting and constructively interfering. Okay, so this person is at a location where there is constructive interference. Let's see the smile on this person's face indicating, yes, that's constructive. I will also introduce another bit too. The low pressure, if you look on the right side, is indicated by dotted line. Roll with me here. Here's the same smiley person in this picture a short time later. Specifically, if you think about it, you'll find out what that time is. But that person will always be at a location of constructive interference, this person with the smile. Constructive interference, no matter what time it is, no matter how long you wait, at any time, that location is a location of constructive interference. I'm emphasizing location and time because sometimes it's easy to get them mixed up. Let's check out this person's friend with the frowny face. I'm going to zoom in, actually, this is better. The frowny face is at a place where there is always destructive interference. And if you think about it carefully, that never changes. It's always destructive interference at that location. So as long as that person stands there, they're going to get destructive interference the whole time. So if you think about it, and I encourage you to do this exercise, though I will not do it for you here, the distance between two frowny faces, which by the way you would perceive as total silence in real life. The distance between two frowny faces is a half a lambda. So here's the picture. You can analyze it if you like and convince yourself that that is true. Okay? This can happen in two dimensions too. This is from the Giancoli textbook. It shows two speakers interfering with each other, and there are locations. You can imagine this, say you're out on a football field and there's two speakers, or maybe you're at a concert and there's two speakers and they're doing the same thing. There are locations that will, at least in theory, be dead quiet, and some that will be loudest, nodes and antinodes. I'm going to show you a couple other people's pictures of these, and stop at the end where I would say that the condition for constructive interference and the condition for destructive interference can be calculated. And there are, of course, many positions. If you do the analysis, you will convince yourself that constructive interference is wherever the difference in distance to each speaker is either, if they're the same distance, that's 0 lambda, or you could go 1 lambda or 2 lambda, and you'll get constructive interference. There's other locations that will be destructive interference, and the condition for that is your delta R has to be 1/2 a lambda, or 3/2 lambda, or 5/2. If you do the analysis, you'll see why this must be true. So that is interference in 2 dimensions. Next, I want to start thinking about time. So now, this is a different picture. My axis here now is time, left to right, time, that's my T, and let's just call that, say, pressure. I'm going to think about air. I'm going to think about sound as a change in pressure in a particular location. We're at 1 location now. So this is a specific location, changing time. And you could see if I put in 2 different frequencies, at sometimes they will line up, and sometimes they will not. So sometimes I get destructive interference, and sometimes I get constructive interference. What you end up with at the bottom is the sum. And you can see it goes from big amplitude down to small amplitude down to big. And that shape, I would call that the envelope of the sound. That is the beat frequency. So there's an equation for that. It's essentially just the difference in the 2 input frequencies. You get a beat at whatever that difference is. Okay? A good way to visualize this is imagine 2 children on a swing set. You push somebody here and they start moving, but maybe somebody else is a different length from the pivot at the top of the swing, and they're moving at a slightly different speed, very slightly. So sometimes they kind of line up, and then after a while they drift apart and they're going opposite each other. That's one way you could visualize using a pendulum, which is children on a swing. I'm going to mention the next topic now, which is Doppler shift. This is the well-known phenomenon where something's approaching you, you get one frequency, and if it's driving away from you, you get a different frequency. You've probably heard this. The classic example is a siren in, you're in a car and some vehicle comes by with making a sound like a siren. Rather than demonstrate that here, I'll point you to some links that have it, and I will tell you one last thing. There is an equation for Doppler. You'll notice there's 4 different equations here. I compress them into 2 using the plus or minus notation, and you can use your common sense to know whether it's the plus or the minus. In fact, it's a good exercise. Like, which one should I use if it's moving toward or away? Like, think about what you would expect to happen to the frequency and then choose the right plus or minus to make it work. So total of 4 equations. I show them into here just to save a little space. I think that's all I've got to say then today about interference, beats, and Doppler. So hang on till the next episode. We're going to be talking about sound measurement soon.